Hi, happy to be here. Thanks, OneSetup, for the introduction. So I have 15 minutes to try to show you what you can do today with folding schemes, but in terms of apps. And the app that you're about to see is like a toy for us, because it basically crosses together a lot of things. zkML, gaming, and of course, folding schemes. So let's check out what we have prepared for you. So the idea is to have a provable Connect4 engine with a baked-in reinforcement learning agent. So, okay, so what does it consist of? It consists of this conceptual equation of like having Connect4 with some kind of reinforcement learning algorithm, some zero knowledge, and you get like this QR code that will guide you to the app. So the idea is to use folding schemes for being able to give players the ability to run some reinforcement learning algorithm while playing Connect4 and being able to actually prove the outcome of their game. And so you might ask, but why are you doing this? Well, actually, there is quite some interesting motivations to do that. The first one is that there was a huge event those days, the Autonomous World event, and today there is a big attractivity of trustless peer-to-peer gaming. But the thing is that games can have two prohibitive kind of costs. The first one is like the prohibitive cost of state transitions. So how much does it cost you to show to people looking at your game that you have actually played the game in a fair way, and costly AI experiences. So it's quite hard to have meaningful AIs running either on-chain or off-chain, although today zkML is kind of starting to grow as a field. And folding schemes can actually help us to do that. And that's because we want users to have rich experiences when they deal with peer-to-peer systems. So this is an experiment to see how folding schemes can help us achieving this. So the first question is, what is a valid Connect4 game? So for that, I see that my numbering system is kind of weird. Maybe you can think of that they are all equally important. Because first thing is that you want players to not play on a non-empty cell. You want them to play also on a cell with other field cells below, so that it's just not hanging around into the Connect4 grid. And you don't want also to have underflowing or overflowing over the columns or the rows, so that you don't end up with some kind of infinite Connect4 game. What does it mean to have a provable reinforcement learning agent? So here we just take the straightforward route of saying that we don't want to deal with training. We are only dealing with inference here. And this is what the circum code that we will use for that, which is a simple, fully connected neural net. And we have used for that the keras2circum library. So the process is quite straightforward. You train your agent using reinforcement learning, you save the weights, and you input the weights within the circuit at inference time. And that's it. Finally, why would you use folding schemes to do that? Well, because you have repeated computations, meaning at each step you are proving that you have done a correct Connect4 state transition and that you have done a correct inference step with the AI agent. So that means that you end up with some big instance for which you have some public inputs and auxiliary outputs, and for that Nova is like fitting our broad idea. So we have a repeated computation. We repeatedly verify that both the RL agent and board transitions are correct. And we also have a large circuit, which makes sense because since we have a fixed cost to pay with recursivity constraints, you want the circuit that you are folding to have some actual cost. So how can you do this if you want to start developing on top of Nova? There is a great library that was written by Nalin, which is called Nova Scotia. And Nova Scotia is a library that acts as a middleware between your circumcircuits and Nova. So you will write your circumcircuit, you will end up with some F here, and then you are basically done. So you compile to R1CS using, for instance, circum. So you end up with some witness generator code and an R1CS file. Then you can prepare your intermediary auxiliary values. So let's say the game you just played against the AI and all the state transition you had with Connect4. And then you plug Nova Scotia on top of that to fold your R1CS instances with all the different witnesses that you have gathered before. One cool thing that you get while working with Nova and Nova Scotia is that you can compile Nova proving to WASM using tools like WASMPack. So that means that you can get like some pretty cool performances within your browser while working with this framework. So this is really the cherry on top of working with the Rust library and of working with Nova. And finally, you can also leverage things like the browser web workers to offload the work out of the browser's main thread so that you are not blocking the user while proving things. And eventually, you end up with something that can actually work. And there was supposed to be a video, and it's here. And is it going to work, or do I need to press another button? I don't know. I think it's not going to work, the video. Are videos supposed to work on the app, or maybe not? We have 8 minutes, so we are good on time. Wow, this could be a long wait. Yes, so if you go to the app, what it's going to do is that you are going to end up with a Connect4 grid. So a 7x6, so it's like a regular Connect4 grid. You will be able to play your Connect4 game, and you end up with some kind of button on the bottom, which will lead you to do two things. The first thing that you will need to do is to download what we call public parameters that will help you generate the proof. And once the public parameters are actually loaded, you can generate the proof for your specific Connect4 game. And so when you end up with the proof, you will be able to show to anyone that you have played a valid Connect4 game and that you have actually beaten the RL agent. So you could imagine a future in which you have a lot of different RL agents floating into the peer-to-peer space, and that you can get a way to prove that you have beaten this particular RL agent and not this particular other RL agent that is really good. You can imagine rankings between RL agents, so that actually can enhance a lot the peer-to-peer gaming space, and that would use, in that case, things like folding schemes. So yeah, everything is done client-side, so you do not need to send anything to some untrusted server. You do all the Connect4 game on your app. You do all of the proving on your app as well. And it seems like it's actually coming. But yeah, it's the video had some editing, so it's okay. We'll skip the video because there is an important slide right after that, and you can actually play the app, which is this working? It's not working anymore. Okay, cool. Oh, okay, yes. Okay, I'm sorry. I will skip to the slide that because actually downloading the public parameters can take time, so I'm not really trusting the Wi-Fi here. So the first idea that you have to take away from that is that folding schemes make provable really costly things. So like zkML is really cheap when using folding schemes. There have been some projects like Zator that have showed that you can pack some 2 billion constraint ML network within a circuit. And here it's like using some, I think it's 150K constraint. So that's quite interesting. So folding schemes can make those things like really cheap. So that's the first idea. So if you have like some big idea with respect to, for instance, snarkifying some huge LLM like Llama or I don't know, some open source LLM, I think that could be doable with folding schemes. So that could be something that would be nice. Also, the snark folding tooling is here. So it's not something that is out of space. Projects can actually start with folding schemes, and using Nova Scotia for that and zkCom is actually a very good starting point. So I encourage you to do that. Also, folding has a large application domain, as we have seen. The first one is zkML, but you have also like things like non-zk friendly hash functions. So some people have actually run benchmarks on non-zk friendly hash functions like SHA-256 and have proven like to have really good performances in terms of cost, hashing huge documents using Nova. It's called Nova SHA-256. You can check the GitHub repo. And of course, you have also things like signature aggregation or even rollups. The final idea is that folding enables rich zk apps, which were not possible before. And I hope that my talk will have demonstrated that. And yes, now there is a thank you slide. Let's go. No. OK, thank you.
Thank you, Pierre, so much for sharing your experience. Questions?
I saw that the size of the circuits in the slides was around 150K for that game. And I wonder, how long did it take to run in the browser of that size of a circuit? And what was the size of the parameters, including maybe the keys for Nova?
Yes, so the size of the parameters is around 2 gigabytes. So that's why I was not really trusting the live demo to like run in some time that is actually interesting for you guys to check. And the proving time, I'm not sure. I'm not sure to remember exactly, but I think it's some proving time that is actually UX doable. Yeah.
Sorry, what was that?
UX doable proving time. I don't have a specific
One
number.
quick follow-up question, though.
Yep.
It's probably because I'm a little bit ignorant on how Nova works, but would the security parameter on Nova, is it expected to grow depending on the size of the circuit, or maybe some other like parameters?
Yes, I think I don't remember also the cost in terms of like how much the public parameters grows in size of the circuit, but I think so. Yeah.
I see. Thanks.